Euler's theorem. If n is any positive integer and GCD of a and n is 1, then a raised to phi of n and 1 are congruent to mod n. This is Euler's theorem. To prove this theorem, we have to first know the Euler's function. What is Euler's function? Euler's function, let phi of n denote the number of positive integer not exceeding n that are relatively prime to n. Then the function phi is called as Euler's function. For example, if we take any number 7, for example, what is phi of 7? We know that the numbers which are less than 7 and relatively prime to 7, that are 1, 2, 3, 4, 5, 6. These are less than 7 and relatively prime to 7. Relatively prime means GCD of this and this are equal to 1. GCD of 1 and 7 is 1, GCD of 2 and 7 is 1, and so on. So how many numbers are there? 1, 2, 3, 4, 5, 6. So phi of 7 is 6. If we take phi of 8, what is phi of 8? Which are relatively prime to 8? 1. 2 is not relatively prime to 8. 3 is relatively prime to 8. 5. And 6 is not relatively prime to 8. 7 is relatively prime to 8. So phi of 8 is 1, 2, 3, 4. So this is we called Euler's function. Now we have to prove Euler's theorem. Consider in the first step, we have to consider that a1, a2 up to a phi of n are less than n and relatively prime to n. Now a1, a2 up to a phi of n, these are the numbers which are less than n and relatively prime to n. Now we consider that ai and aj are congruent to mod n. Here a is what they given, GCD of a and n is equal to 1, and ai and aj belongs to the set a1, a2 up to a phi of n. ai and aj are belongs to this set, which the numbers which are less than n and relatively prime to n. Here ai and aj are not equal, they are different numbers. Now if we consider this equation, what this says, any two of these numbers with multiplying with a, that leaves the same remainder when divided by n. But this is not correct. We are assuming that if here GCD of they given GCD of a and n are equal to 1, they are given. If GCD of a and n are equal to 1, then this equation, this congruent relation can be written as ai and aj are congruent to mod n. Now what is this means? This means that n divides ai minus aj. We know that ai and aj are not equal, so this is not equal to 0, and also ai and aj are less than n and relatively prime to n. So this difference cannot be divided by n. This is impossible. So this is contradiction. By this we can say that a1, a into a1, a into a2 up to a into a phi of n leaves different remainders. when divided by n. Now the next step is, we know that if we divide a1 a into a1, we get any remainder a1 dash, that can we write here mod n. If we divide a into a1 by n, we get some remainder a1 dash. We can write it in this way, in terms of congruences. Now what this is, now here we know that they given GCD of a and n is equal to 1. Here GCD of a and n is equal to 1, and we are taking that a1 a2 up to a phi of n are relatively prime to n. So GCD of a1 and n are also equal to 1. What this is, GCD of a into a1 and n are equal to 1, because GCD of a and n are equal to 1. Similarly, GCD of a1 and n are equal to 1. Then GCD of a into a1 and n are equal to 1. By this, if GCD of a into a1 and n are equal to 1, then what it becomes, GCD of a1 dash and n are also equal to 1. If GCD of we are here taking that a1 dash is less than n, this says that a1 dash and n are relatively prime. This shows that a1 dash belongs to any of a1 a2 up to a phi of n. a1 dash lies in any number in this. If we divide a into a2 by n, we get a2 dash as a remainder. This is different from a1 dash, but it lies in between any one of a1 a2 up to a phi of n. But a1 dash is not equal to a2 dash. Similarly, if we continue this process up to a into a phi of n, we get a dash phi of n remainder, and this is also belongs to this set. This means that if we multiply all these congruences, we get a into a1, a into a2 up to a into a phi of n, that is congruent to a1 dash into a2 dash up to a phi of n dash mod n. If we do these are phi of n different reminders, so we can write instead of this a1 a2 up to a phi of n, because these are belong to this set and these are different. So we can write instead of this. So a into a1 to a into a phi of n, a1 into a2 into up to a phi of n mod n. Now here a is repeated phi of n times, so we can write a raised to phi of n into a1 into a2 into up to a phi of n. Here also a1 into up to a phi of n mod n. Now we know that a1 to a phi of n, these are less than n and relatively prime to n. Relatively prime means GCD of a1 into a2 into up to a phi of n and n are equal to 1. If GCD is 1, then we can write it as a raised to phi of n and 1 are congruent to mod n. This is by property of congruences. So this is what Euler's theorem says. Hence the proof.